Two massive galaxies are locked in a death spiral right now. This collision should destroy everything in its path. Instead, it's creating stars faster than should be possible. Tonight we're discovering why cosmic crashes become star factories, how destruction becomes creation on the largest scales imaginable. Before we dive into this cosmic demolition zone, drop a comment about your favorite space phenomenon. If these deep space explorations fascinate you, consider subscribing. These journeys into cosmic chaos are meant to be shared. Something strange appears when you point powerful telescopes toward a distant part of space. Two enormous trails stretch outward like insect antennae. They extend far beyond where any normal galaxy should end. These galaxies earned their nickname from this bizarre shape. Scientists call them the Antennae Galaxies. The trails contain billions of stars that were ripped away from their home galaxies. Here's what created these cosmic antennae. When two galaxies get close, gravity works differently on different parts. The near side feels stronger pull than the far side. This difference literally stretches each galaxy like taffy. Stars and gas get pulled out in long streams. These streams become the antennae we observe today. The collision didn't just tear material away from both galaxies. It flung billions of stars into empty space, creating structures that span hundreds of thousands of light years. The center of this collision blazes with colors you'd never expect. Brilliant blue regions shine alongside bright pink clouds. These aren't just pretty cosmic decorations. Each color tells us exactly what's happening. Blue light comes from brand new stars. The hottest, most massive stars shine blue-white. These stellar giants burn their fuel incredibly fast and die young. The pink glow comes from gas clouds. When those hot blue stars shine on hydrogen gas, something remarkable happens. The starlight energizes the hydrogen atoms. They respond by glowing pink. The brighter the pink, the more massive stars are being born nearby. This combination reveals something extraordinary. These galaxies are creating new stars at rates 10 to 100 times faster than normal. Scientists have a name for this phenomenon. They call it a starburst. It means the galaxies are burning through their star-making material so fast they'll run out in just hundreds of millions of years. These weren't always colliding galaxies. For billions of years, they lived as separate spiral galaxies. Each had beautiful curved arms and orderly rotation. Then something changed their fate forever. Gravity brought them together. Not quickly, but over hundreds of millions of years. Like dancers in an extremely slow waltz, each galaxy began to feel the other's gravitational pull across vast distances. The first close approach happened roughly 300 million years ago. That's when the real drama began. Neither galaxy could escape the other's grip. They were locked together by invisible gravitational chains. Now they're spiraling inward toward their final merger. Each orbit brings them closer together. The dance will end when both galaxies completely merge into something entirely new. Two ancient spiral galaxies are transforming into one chaotic, star-forming monster. Normal galaxies create new stars at a steady, predictable pace. Think of it like a factory running at normal speed, but the Antennae Galaxies have shifted into overdrive. The collision compressed gas clouds throughout both galaxies. When you compress gas, it becomes denser. Dense gas can collapse under its own gravity. That's exactly what triggers new star formation. But here, it's happening everywhere at once. Massive star clusters are being born by the hundreds. Each cluster contains hundreds of thousands of new stars packed into tiny regions. Some of these stellar nurseries outshine entire normal galaxies. This star formation frenzy can't last forever. The galaxies are consuming their gas supplies at an unsustainable rate. They're experiencing what astronomers call a starburst phase. It's like a cosmic baby boom that will exhaust itself within a few 100 million years. The most dramatic features of this collision aren't at the center. They're the two enormous tails of material streaming away from both galaxies. These cosmic streamers stretch across distances that dwarf our entire solar system. How do entire streams of stars get flung into empty space? The answer lies in how gravity works during galactic encounters. As the galaxies swing past each other, different parts experience different gravitational pulls. Stars on the outer edges of each galaxy feel this difference most strongly. Some get accelerated and flung outward. Others get decelerated and fall inward. The result is two distinct tails of stars and gas streaming in opposite directions. These tails aren't just debris. Astronomers have discovered that some regions within the tails are actually forming new stars. Gravity is still working even in these scattered streams, pulling material together into dense knots where star formation can begin. The collision didn't just destroy the original galaxy structure. It created new places where stars can be born. The collision didn't just destroy the original galaxy structure. It created new places where stars can be born. This collision didn't happen overnight. It's a story that spans more time than complex life has existed on Earth. The drama began when both galaxies were still pristine spirals, each minding its own business in deep space. About 300 million years ago, gravity finally pulled them close enough for their first encounter. Picture two cosmic dancers beginning an elaborate, deadly dance. Neither could escape once they got within each other's gravitational influence. That first close passage created the initial distortions we see today. It's when the antennae first began to form. The galaxies swung past each other, got stretched and twisted, then continued on elongated orbits that would bring them together again. Each subsequent passage has been closer than the last. The orbits are decaying, spiraling inward like water going down a drain. The final merger is still millions of years away, but the outcome is already decided. These two spiral galaxies will become one giant elliptical galaxy, forever changed by their violent encounter. When astronomers first studied these colliding galaxies, they discovered something puzzling. The combined system was much brighter than you'd expect from simply adding two normal galaxies together. The collision was somehow making everything shine more intensely. The answer lies in the star formation explosion happening throughout both galaxies. All those newly born massive stars pump out enormous amounts of energy. Blue giant stars can outshine our sun by factors of thousands or even millions. But there's more to the story. The collision also stirred up vast amounts of dust throughout both galaxies. This cosmic dust absorbs starlight and re-emits it as heat radiation. That makes the galaxies much brighter in infrared light than normal galaxies. The combination creates a cosmic lighthouse effect. The Antennae Galaxies can be observed across much greater distances than typical spiral galaxies. This brightness makes them perfect laboratories for studying what happens when galaxies collide. We're witnessing galactic evolution in action. For billions of years, each galaxy maintained beautiful spiral structure. Curved arms wound outward from central bulges. Stars followed orderly orbits. Everything had its place in a cosmic dance of remarkable precision. The collision destroyed all of that ancient order. Spiral arms got twisted and torn apart. Stellar orbits became chaotic and unpredictable. The neat disk structure that defined each galaxy began to dissolve into something resembling cosmic chaos. This destruction isn't random, though. It follows physical laws that govern how matter behaves when massive objects interact gravitationally. Stars don't actually collide during galactic mergers. Space is too vast for that. But their orbits get completely scrambled. The end result will be something entirely different from where this story began. Instead of two orderly spiral galaxies, this collision will produce one giant elliptical galaxy. All traces of the original spiral structure will be erased. Billions of years of galactic architecture will be replaced by a new, more chaotic arrangement. The Antennae Galaxies sit at just the right distance from Earth for scientific investigation. They're close enough that our most powerful telescopes can resolve individual star-forming regions. But they're far enough away that we can see the entire collision system in one view. This distance is roughly 65 million light-years from Earth. In cosmic terms, that makes them relatively nearby neighbors. Close enough that the Hubble Space Telescope can pick out individual star clusters within the collision zone. Being this close gives astronomers an unprecedented opportunity. We can study galactic collisions in amazing detail. We can map where new stars are forming, measure how fast the galaxies are moving, and track how the merger is progressing over time. The antennae have become the most thoroughly studied example of colliding galaxies in the universe. They serve as a cosmic laboratory for understanding what happens during galactic encounters. Every new observation teaches us more about these violent but creative events. What you see in visible light is only part of the story. The most dramatic action in the Antennae Galaxies is actually hidden from our eyes. It's happening in a type of light we can't see naturally: infrared radiation. All that dust stirred up by the collision does something remarkable. It absorbs the light from hot new stars and re-radiates that energy as heat. This makes the galaxies incredibly bright in infrared wavelengths, much brighter than typical galaxies. Infrared space telescopes reveal star formation happening behind thick curtains of dust. Regions that look dark and empty in visible light turn out to be stellar nurseries working over time. The collision created perfect conditions for this hidden star formation. This infrared excess tells astronomers that we're witnessing one of the most intense star formation events in the nearby universe. The antennae are converting gas into stars at a rate that few galaxies can match. They're cosmic furnaces running at maximum output. The Antennae Galaxies show us more than just what happens when galaxies collide. They offer a preview of our own cosmic future. Our Milky Way galaxy is headed for a similar collision with the Andromeda Galaxy. That future collision is still billions of years away. But when it happens, it will look very much like what we observe in the antenna system today. Two spiral galaxies locked in a gravitational death spiral, creating stars at extraordinary rates. Astronomers have used computer simulations to model what our galactic collision will look like. The results bear striking resemblance to the Antennae Galaxies. We're essentially looking at our own distant future playing out in real time. This gives the antennae special significance in astronomy. They're not just an interesting cosmic curiosity. They're a time machine that shows us what galactic evolution looks like when massive star systems merge. In studying them, we learn about the ultimate fate awaiting our own corner of the universe. How do galaxies that start billions of light years apart end up in a death spiral? The answer lies in the invisible threads that connect everything in the universe. Gravity never stops working, no matter how vast the distances involved. These two galaxies didn't start close together. For most of their lives, They were separate spiral galaxies minding their own business. But gravity was already at work, pulling them slowly together across cosmic distances. The galaxies followed what astronomers call parabolic orbits. Think of it like two ships on a collision course in slow motion. Each galaxy moved through space on a path that would eventually intersect with the other. The journey took billions of years. Once they got close enough, their gravitational fields overlapped. That's when both galaxies became trapped. Neither could escape the other's pull. They were locked together by invisible chains that span hundreds of thousands of light years. The universe's strongest force had claimed two victims for its longest dance. The moment of first contact wasn't gentle. When these two massive galaxies swung past each other for the first time, the gravitational forces unleashed were beyond comprehension. This single event triggered all the chaos we observe today. Picture what happens when a massive object suddenly appears next to another massive object. Every star, every gas cloud, every piece of matter feels the newcomer's gravitational pull. But the pull isn't uniform across such enormous structures. Stars on the side facing the approaching galaxy feel stronger attraction. Stars on the far side feel weaker pull. This difference stretches both galaxies like cosmic taffy. That's how the famous antennae tails first formed during this initial flyby. The first passage also compressed gas clouds throughout both galaxies. Compressed gas is exactly what you need to trigger massive star formation. One gravitational encounter created the conditions for the star formation explosion we see today. The galaxies will never be the same after this cosmic collision. Once locked in this gravitational embrace, both galaxies face an inevitable fate. They're losing energy with every orbit. Like water spiraling down a drain, they're being pulled inexorably toward their final merger. This happens because of something called orbital decay. Each time the galaxies swing past each other, they lose a tiny amount of energy. That lost energy gets converted into gravitational waves that ripple out through space-time itself. As they lose energy, their orbits get smaller and smaller. Each passage brings them closer together than the last. It's a one-way process that can only end in complete merger. No force in the universe can reverse this spiral toward destruction. The process also gets faster as time goes on. Early orbits took hundreds of millions of years. Later orbits happen much more quickly. The final merger will occur in a cosmic instant compared to the billions of years it took to reach this point. Gravity always wins in the end. Speed determines everything in this cosmic collision. When objects weighing hundreds of billions of times more than our sun move at incredible velocities, the energy involved defies human comprehension. These aren't gentle encounters. The galaxies approach each other at speeds measured in hundreds of kilometers per second. To put that in perspective, that's faster than anything humans have ever built. It's speed that would cross entire continents in minutes. At the moment of collision, all that motion gets converted into other forms of energy. Kinetic energy becomes heat. It triggers shock waves. It compresses gas clouds beyond their normal densities. The collision literally shakes both galaxies down to their cores. This tremendous speed explains why the collision creates such dramatic effects. Gentle encounters might barely disturb galactic structure. But at these velocities, the gravitational forces involved can reshape entire star systems and fling material across hundreds of thousands of light years. Unlike many galactic encounters, this collision involves two galaxies of roughly equal mass. That balance makes all the difference in creating the spectacular display we observe today. both galaxies get severely disrupted instead of just one. When a small galaxy collides with a large one, the result is usually one-sided destruction. The small galaxy gets torn apart while the large one stays mostly intact. But here, both galaxies pack enough gravitational punch to seriously damage each other. This symmetry creates the double-tailed structure that gives the antennae their name. Each galaxy contributes one tail to the cosmic display. Both spiral structures get equally twisted and distorted. Neither galaxy dominates the interaction. The balanced encounter also explains why star formation explodes throughout the collision zone rather than in just one location. Equal mass collisions create shock waves and compression throughout both galactic disks. The result is a star formation frenzy that affects hundreds of billions of stars across both systems. Inside each galaxy, billions of stars suddenly find themselves in an impossible situation. They're no longer dealing with the simple, predictable gravity of their home galaxy. Now they feel gravitational pulls from multiple directions at once. This creates what physicists call the three-body problem. One star feeling gravity from two massive galaxies at the same time. The mathematics become incredibly complex. Stellar orbits that were once predictable become completely chaotic. Some stars get accelerated and flung outward into space. Others get decelerated and spiral inward toward the galactic centers. Many stars find themselves on wildly eccentric orbits that take them far from their original neighborhoods. The chaos affects every single star in both galaxies. Orbits that took hundreds of millions of years to complete get scrambled in cosmic instants. The orderly rotation that characterized both spiral galaxies dissolves into gravitational pandemonium. Simple physics gives way to cosmic complexity that can only be solved by supercomputers. The way these galaxies approached each other wasn't random. The angle and orientation of their encounter determines how much of their original structure survives the collision. This wasn't a head-on crash, but something more complex. Computer simulations show that head-on collisions destroy spiral structure almost immediately. But angled encounters can preserve some galactic architecture for much longer periods. The antennae represent this more gradual type of collision. The galaxies approached each other at an angle that allowed their spiral arms to survive the initial encounters. That's why we can still see hints of their original structure in current observations. A purely head-on collision would have erased those features long ago. This encounter geometry also determines where the most dramatic star formation occurs. Angled collisions create compression zones in specific regions rather than throughout both galaxies uniformly. The result is the patchy, irregular pattern of stellar nurseries we observe today. When two galaxies pass close to each other, every star experiences a brief but powerful gravitational shock. It's like a cosmic earthquake that lasts for millions of years. This single event permanently alters the orbit of every affected star. The shock happens because gravitational attraction changes rapidly as the galaxies swing past each other. One moment a star feels weak pull from the distant galaxy. The next moment, as that galaxy swoops closer, the gravitational force increases dramatically. This sudden change in gravitational force acts like a cosmic impulse. It gives every star a gravitational kick that changes its orbit forever. Stars that lived in the galactic suburbs suddenly find themselves on paths toward the center or flung outward toward the edges. The effect is permanent and irreversible. Even after the galaxies move apart again, the stars remember their gravitational shock. Their new orbits reflect that brief but intense encounter. The organized stellar traffic of two spiral galaxies transforms into the chaotic orbits of a future elliptical galaxy. Galactic collisions can't be rushed. The time scales involved dwarf human comprehension. From first encounter to final merger takes roughly 1 billion years. That's long enough for entire species to evolve and go extinct multiple times on planetary surfaces. The extended timeline comes from the sheer scale of the objects involved. Galaxies are so massive and so large that even at tremendous speeds, it takes an incredibly long time for the collision to play out completely. Think of it as the universe's slowest car crash. During this billion-year merger process, the galaxies make multiple passes by each other. Each encounter brings them closer together and increases the damage to their spiral structures. The final merger represents just the last chapter of a very long story. This extended timescale means we're seeing just one snapshot of an ongoing process. The dramatic features we observe today will continue to evolve for hundreds of millions of years more. The collision that began 300 million years ago won't reach its conclusion until our sun has aged considerably. How do astronomers study an event that takes 1 billion years to complete? They use the most powerful supercomputers on Earth to run detailed simulations. These computer models can compress 1 billion years of galactic evolution into months of calculation. The simulations start with two pristine spiral galaxies and let physics take over. Gravity acts on millions of simulated particles representing stars and gas clouds. Slowly, over thousands of computer hours, the collision plays out in fast motion. These digital recreations match the real Antennae Galaxies with remarkable accuracy. The computer models reproduce the tail structures, the star formation patterns, and even the timing of major events. They give us confidence that we understand the physics involved. The simulations also let astronomers peek into the future. They show what the antennae will look like millions of years from now. The final product will be a single large elliptical galaxy, with all traces of the original spiral structure erased. Computer models reveal both the past and future of this cosmic collision. What happens when gravity from outside becomes stronger than gravity from within? Every galaxy has a hidden boundary where its own gravitational control breaks down completely. Cross that line and material starts escaping into space forever. This invisible boundary exists around every massive object in the universe. Scientists call it the zone of tidal instability. Beyond this point, differential gravity takes over. That means different parts of the same object feel different amounts of gravitational pull. For the Antennae Galaxies, this breaking point became catastrophic during their close encounters. Stars and gas clouds in the outer regions felt stronger pull from the approaching galaxy than from their own galactic center. That difference was enough to overcome billions of years of gravitational loyalty. Once material crosses this tidal boundary, it can never return home. The escape matter streams away from both galaxies, forming the magnificent tail structures we observe today. Tidal instability transformed galactic citizens into cosmic refugees, forever banished from their original neighborhoods. Every galaxy defends itself against gravitational theft through an invisible barrier called the Roche limit. This represents the closest another massive object can approach before tidal forces overwhelm the galaxy's ability to hold on to its outer material. Think of it like a cosmic tug-of-war. On one side, the galaxy's own gravity tries to keep everything bound together. On the other side, the approaching galaxy's gravity tries to steal material away. The Roche limit marks where the thief becomes stronger than the defender. For spiral galaxies like the original Antennae, This limit extends far beyond the visible disk. Gas clouds and outer stars orbit in regions where galactic gravity is already weak. When another massive galaxy approaches, these outer regions become the first casualties of tidal warfare. The Roche limit isn't fixed in stone. It depends on the masses and densities of both objects involved. During the Antennae collision, both galaxies had similar masses, so their Roche limits overlapped significantly. That overlap zone became the battlefield where tidal forces won their greatest victories. One of the antennae's tails stretches forward in the direction of orbital motion. This isn't random cosmic debris. It's a gravitational prediction made visible in stars and gas. The leading tail shows us exactly where these galaxies are headed in their cosmic dance. This forward tail forms through a counterintuitive process. During close approach, some material gets accelerated beyond its normal orbital speed. Instead of falling inward like you might expect, this accelerated matter gets flung outward ahead of the galaxy's motion. The leading tail essentially maps the future orbital path of the galaxy system. Follow its curve, and you're tracing where gravitational mechanics will carry these colliding galaxies over the next several million years. It's like a cosmic roadmap written in scattered stars. Astronomers use this leading structure to test their computer models of galactic encounters. If the simulations correctly predict the shape and direction of the leading tail, it confirms that scientists understand the physics governing this cosmic collision. The tail becomes a test of our knowledge about how gravity sculpts the universe. Behind each galaxy stretches a trailing tail that tells a different story. While the leading tail predicts the future, the trailing tail preserves the past. It's a stellar archaeological record of where these galaxies have already been in their gravitational dance. The trailing tail forms from material that gets decelerated during galactic encounters. Instead of speeding up like the leading tail material, these stars and gas clouds slow down relative to their parent galaxy. Gravity then pulls this slower material backward along the orbital path. This creates a permanent record of the collision's history. The shape and extent of the trailing tail reveal details about previous close encounters. Scientists can read this cosmic fossil record to reconstruct exactly how the galactic collision unfolded over hundreds of millions of years. Each bend and twist in the trailing structure corresponds to a specific gravitational event in the collision timeline. The tail preserves information about orbital velocities, approach angles, and the timing of close encounters. It's like having a cosmic flight recorder that documents every major event in this billion-year catastrophe. The two antennae tails look remarkably different from each other. One curves gracefully in a smooth arc. The other appears more twisted and complex. This asymmetry reveals hidden details about how the collision unfolded and what each galaxy contributed to the cosmic chaos. Several factors create this lopsided appearance. The galaxies didn't approach each other head-on, but at an angle that favored one side over the other. Their masses, while similar, weren't perfectly identical. Even small differences get amplified into dramatic asymmetries over cosmic timescales. The collision angle determines which parts of each galaxy experience the strongest tidal forces. A slightly tilted encounter means one galaxy's outer regions get more severely disrupted than the others. This creates tails of different lengths and shapes from otherwise similar parent galaxies. Mass ratio differences also contribute to the asymmetry. Even if one galaxy is only slightly more massive than the other, that small advantage translates into stronger gravitational influence during close encounters. The more massive galaxy creates longer, more extensive tails while suffering less severe disruption itself. During tidal disruption, something unexpected happens. Stars and gas clouds don't stay together, even though they started in the same galactic neighborhoods. The collision sorts different types of material into separate streams based on how they respond to gravitational forces. This separation occurs because stars and gas have different properties. Individual stars are dense, compact objects that respond predictably to gravitational forces. Gas clouds are diffuse and can be influenced by additional factors like pressure and magnetic fields. When tidal forces start working, stars follow precise gravitational trajectories determined by their positions and velocities. Gas clouds, however, can be compressed, heated, or swept along by stellar winds from nearby hot stars. These additional forces cause gas and stars to take diverging paths through space. The result is a complex tail structure where stellar streams and gaseous streams occupy different regions. Astronomers can map these separated components using different types of telescopes. The separation reveals how various forms of matter behave during the universe's most violent gravitational encounters. Tidal tails aren't random sprays of cosmic debris. They follow specific paths determined by the gravitational landscape created during galactic encounters. These invisible highways channel escaping material into organized streams that stretch across hundreds of thousands of light years. The streams form along what physicists call gravitational equipotentials. These are regions where the combined gravity from both galaxies creates natural flow patterns. Material released from the galaxies naturally follows these gravitational channels, like water flowing downhill. Understanding these stream dynamics helps astronomers predict where tidal material will end up. Some streams will eventually disperse into intergalactic space. Others might reconnect with the merged galaxy system millions of years in the future. The streams also concentrate material into dense filaments rather than spreading it uniformly through space. This concentration effect can actually trigger new episodes of star formation within the tails themselves. Gravity continues to work even in the scattered debris, pulling material together into star-forming knots. The most dramatic tidal effects happen when the galaxies reach their closest approach during each orbital pass. At this moment, called pericenter, tidal forces reach maximum strength. Stars and gas clouds that survived previous encounters finally get ripped away from their home galaxies. This timing isn't coincidental. Tidal forces depend on distance, and they get stronger as objects move closer together. During the closest approach, the difference in gravitational pull between near and far sides of each galaxy becomes overwhelming. Pericenter represents the moment of maximum vulnerability for both galactic systems. Material that managed to stay bound during earlier, more distant passages finally reaches its breaking point. The closest approach becomes a cosmic harvest where tidal forces claim their greatest prizes. This explains why the most prominent features of both tidal tails trace back to specific close encounter events. Each major bend or extension in the tail structure corresponds to material that got liberated during a particular pericenter passage. The tails preserve a timeline of gravitational catastrophe. Even in the scattered debris of the tidal tails, gravity finds ways to create rather than just destroy. Bright knots of star formation appear throughout both tail structures, proving that stellar birth can occur even in the most chaotic cosmic environments. These knots form when stream material gets compressed by its own gravity or by interactions with other streams. Even though the material has been ejected from its home galaxy, It can still clump together if local densities become high enough to trigger gravitational collapse. The process creates some of the most isolated star-forming regions in the known universe. These stellar nurseries exist hundreds of thousands of light-years from any major galaxy. They're cosmic islands where new stars are born in the aftermath of galactic destruction. Studying these knots teaches astronomers about star formation under extreme conditions. The newborn stars in tidal tails face a lonely future, far from the gravitational influence of any major galactic system. They represent star formation pushed to its absolute limits by cosmic violence. Something unexpected gets dragged along with the stars and gas in tidal tails. Magnetic fields, invisible threads that permeate both original galaxies, get stretched and carried away by the tidal streams. These fields influence how gas behaves in the scattered debris. Magnetic fields act like cosmic glue that can hold ionized gas together even as tidal forces try to tear it apart. When gas clouds get stretched into long streams, their embedded magnetic fields get stretched too, creating invisible filaments that guide the flow of material. This magnetic dragging effect helps explain why gas streams in tidal tails often appear more organized than pure gravitational dynamics would predict. The magnetic fields provide an additional structuring force that can channel gas flow and prevent complete dispersal. The stretched magnetic fields can also influence star formation within the tails. They can either help compress gas clouds into star-forming knots or prevent compression by providing magnetic pressure that resists gravitational collapse. Magnetism adds another layer of complexity to an already chaotic process. Not all tidal tail material is lost forever. Computer simulations suggest that some of the scattered debris might eventually find its way back to the merged galaxy system. It's like a cosmic recycling program that operates over hundreds of millions of years. This recycling happens because tidal streams don't escape to infinite distances. Many streams follow elongated orbits that carry them far from the merger site, but eventually curve back toward the gravitational influence of the combined system. It's orbital mechanics on the largest possible scales. The returning material could provide fuel for future episodes of star formation in the merged galaxy. Instead of being permanently lost, some tidal debris becomes a delayed delivery system that brings raw materials back to the galaxy after the violence of the initial collision has subsided. However, this recycling process is extremely slow and inefficient. Most simulations suggest that only a small fraction of tidal material actually returns. The majority gets dispersed into intergalactic space, becoming part of the thin web of matter that connects galaxy clusters across cosmic distances. We can see the Antennae's spectacular tidal display because of pure cosmic luck. The orientation of the collision relative to Earth provides an almost perfect viewing angle for studying tidal tail formation. A different angle might have hidden this cosmic masterpiece entirely. The galaxies are oriented so that both tidal tails stretch across our field of view rather than pointing directly toward or away from us. This sideways perspective lets astronomers measure the full extent and structure of both tail systems. It's like having front-row seats to the universe's greatest demolition show. If the collision were oriented differently, the tails might appear foreshortened or completely invisible from our vantage point. We might see only the central collision zone without realizing that magnificent tidal structures extend far beyond the galaxy cores. This fortunate alignment makes the Antennae Galaxies the best laboratory for studying tidal tail physics in the observable universe. The perfect viewing angle combined with relatively close distance gives astronomers unprecedented detail about how gravity sculpts matter during galactic encounters. Sometimes the universe provides exactly the right cosmic experiment at exactly the right angle for human observers. Imagine invisible waves crashing through space at incredible speeds. These aren't ocean waves, but shock waves created by the galactic collision itself. They compress gas clouds throughout both galaxies, triggering the most intense period of star formation either galaxy has ever experienced. Normal gas clouds in space are incredibly thin and cold. They drift peacefully through galaxies for millions of years without forming stars. But shock waves change everything by squeezing these clouds far beyond their natural density limits. When gas gets compressed rapidly, it reaches what astronomers call the critical density threshold. This is the point where gravity becomes strong enough to overwhelm gas pressure and cause the cloud to collapse inward. It's like crossing a line from stability to inevitable stellar birth. The collision created shock waves throughout both galactic disks simultaneously. Every gas cloud, no matter how stable it seemed before, suddenly found itself getting squeezed by forces that dwarf anything in a normal galaxy. The shock waves turned both galaxies into cosmic pressure cookers designed to manufacture stars at breakneck speed. Astronomers have a specific name for what's happening in the Antennae Galaxies. They call it a starburst event. This technical term describes star formation that occurs at rates so extreme they shouldn't be sustainable under normal galactic physics. A starburst means these galaxies are creating new stars at least 10 times faster than typical spiral galaxies. Some regions are forming stars at rates 100 times higher than normal. It's like comparing a gentle rainfall to a torrential downpour. Normal galaxies pace themselves. They form stars steadily over billions of years, carefully managing their gas supplies like a savings account with regular withdrawals. Starburst galaxies burn through their resources like lottery winners on a spending spree. The antennae represent one of the most intense starburst events in the nearby universe. They're converting their available gas into stars so rapidly that this feeding frenzy will exhaust their supplies in just hundreds of millions of years. It's cosmic star formation pushed to its absolute physical limits. Throughout the collision zone, brilliant pink clouds announce the presence of the universe's most massive newborn stars. These glowing regions, called H2 regions by astronomers, mark places where stellar birth is happening at its most dramatic scale. The pink color comes from hydrogen gas that's been energized by incredibly hot, newly formed stars. These stellar monsters are so hot they emit ultraviolet light invisible to human eyes. When this UV radiation hits nearby hydrogen, it causes the gas to glow pink. H2 regions serve as cosmic birth announcements. They only appear around the most massive stars because smaller stars don't produce enough ultraviolet energy to ionize hydrogen gas. The brighter the pink glow, the more massive stellar giants have just been born in that location. The antennae contain hundreds of these pink stellar nurseries scattered throughout the collision zone. Each one represents a location where the galactic compressed gas so effectively that it triggered the birth of stars massive enough to light up their entire neighborhoods with characteristic pink radiation. Some regions in the antennae aren't just forming individual stars. They're creating what astronomers call superstar clusters. These are stellar cities containing hundreds of thousands of stars packed into regions smaller than the distance between our Sun and its nearest stellar neighbors. Think of normal star formation like houses scattered across suburban neighborhoods. Superstar clusters are like Manhattan skyscrapers packed with stellar residents. The density of stars in these regions defies everything we observe in typical galactic environments. These monster clusters form when shock waves compress enormous gas clouds all at once. Instead of fragmenting into many small star-forming regions, the entire cloud collapses together. The result is stellar birth on a scale that creates some of the most crowded neighborhoods in the universe. Each superstar cluster in the antennae contains enough stars to outshine entire normal galaxies. They represent star formation efficiency pushed to its maximum possible level. The collision didn't just trigger star birth. It created stellar metropolises that redefine what's possible in cosmic architecture. Star formation in the antennae doesn't happen in isolation. The first generation of massive stars triggers a chain reaction that spreads stellar birth throughout both galaxies like cosmic wildfire. Each new star helps create conditions for the next generation. Massive stars live fast and die violently. They blast powerful stellar winds throughout their brief lives, then explode as supernovae when their fuel runs out. Both processes compress nearby gas clouds, triggering additional rounds of star formation. This creates a cascade effect where star birth triggers more star birth. Stellar winds from one generation compress gas for the next generation. Supernova shockwaves squeeze even more distant clouds. The process becomes self-sustaining across vast regions of both galaxies. The chain reaction explains why starburst activity spreads throughout the collision zone rather than remaining confined to the initial impact regions. Each stellar generation plants the seeds for future generations, creating a wave of star formation that propagates through both galactic systems over millions of years. The extreme conditions in colliding galaxies don't just accelerate star formation. They actually change what kinds of stars get created. The antennae are producing a higher fraction of massive stars than normal galaxies, creating a stellar population that's fundamentally different from typical galactic residents. This happens because collision environments favor the formation of high-mass stars. The intense compression and turbulence created by galactic encounters make it easier for gas clouds to accumulate enough material to birth stellar giants. Normal, gentle star formation produces mostly smaller, lighter stars. Astronomers call this change in stellar demographics an altered initial mass function. It's a technical term that describes how the collision is shifting the cosmic factory toward producing bigger, more powerful stars than usual. The assembly line has been retooled for manufacturing giants. This shift toward massive stars has profound consequences for both galaxies. Massive stars burn brighter, live shorter lives, and die more violently than typical stars. They flood their surroundings with intense radiation and eventually explode as supernovae. The collision is creating a stellar population destined for dramatic lives and spectacular deaths. Inside every massive star lies a nuclear furnace that creates the heavy elements essential for planets and life. The antennae's population of stellar giants is accelerating this cosmic alchemy at unprecedented rates, producing and distributing heavy elements faster than any normal galaxy. Massive stars burn through their nuclear fuel at incredible speeds. They fuse hydrogen into helium, helium into carbon, carbon into oxygen, and continue building heavier elements all the way up to iron. The more massive the star, the faster this nuclear cooking proceeds. When these stellar giants die as supernova, they scatter their newly created heavy elements throughout space. These explosions seed the surrounding gas with carbon, oxygen, silicon, and dozens of other elements that didn't exist when the universe began. It's cosmic recycling on the grandest scale. The abundance of massive stars in the antenna means this element production is happening at rates far above normal galactic standards. The collision has created ideal conditions for accelerated cosmic chemistry. Both galaxies are enriching their gas supplies with heavy elements at speeds that normal spiral galaxies can't match. The countless massive stars being born throughout the antenna flood both galaxies with ultraviolet radiation invisible to human eyes. This high-energy starlight transforms the entire galactic environment, ionizing gas clouds and heating material throughout the collision zone. Ultraviolet radiation from hot, massive stars carries far more energy than the gentle visible light from stars like our Sun. When UV photons strike atoms in space, they can knock electrons completely free, creating ionized gas that behaves very differently from normal matter. This ionization process affects every gas cloud in both galaxies. Previously cold, dark molecular clouds become hot, glowing regions visible across the electromagnetic spectrum. The collision zone transforms from a collection of cold gas reservoirs into a brilliant stellar showcase. The intense UV environment also influences future star formation. Ionized gas is much harder to compress than cold molecular gas. The massive stars being born today are actually making it more difficult for future generations of stars to form. They're gradually sterilizing their own galactic environments through their energetic output. Both antennae galaxies are changing color before our eyes. What started as reddish spiral galaxies dominated by older, cooler stars is transforming into brilliant blue systems blazing with the light of hot, newly formed stellar giants. This color evolution tells the story of the collision in visual terms. Red light comes from older, cooler stars that were already present before the encounter began. Blue light emerges from hot, massive stars being born in response to the gravitational chaos. The shift from red to blue maps the transformation from old to new. Galaxy color serves as a cosmic clock. Red galaxies have typically finished most of their star formation and settled into middle age. Blue galaxies are actively forming stars and represent cosmic youth and vigor. The antennae are experiencing a dramatic transition from maturity back to stellar adolescence. This color transformation will reverse itself once the starburst phase ends. As the massive blue stars age and die, and as gas supplies become exhausted, both galaxies will eventually return to redder colors. But for now, they're experiencing a brilliant blue renaissance triggered by their gravitational encounter. Normal galaxies are surprisingly inefficient at converting their gas supplies into stars. Most gas drifts through galactic disks for billions of years without ever participating in star formation. The antenna collision has revolutionized this process, achieving star formation efficiency that far exceeds normal galactic standards. In typical spiral galaxies, only a small percentage of available gas actually becomes incorporated into stars during any given time period. Most gas remains unused, waiting for the slow, gentle processes that govern normal star formation. It's like a factory running at partial capacity. The collision changed everything by compressing gas throughout both galactic disks simultaneously. Instead of waiting for natural turbulence to slowly gather material into star-forming clumps, shock waves forcibly compressed gas on galactic scales. The cosmic factory shifted into overdrive. This enhanced efficiency explains why the antennae can sustain such extreme star formation rates. They're not just forming stars faster, they're making better use of their available raw materials. The collision converted both galaxies from inefficient star factories into highly optimized stellar production facilities. This incredible star formation bonanza cannot last forever. The antennae are consuming their gas supplies at such extreme rates that they're guaranteed to exhaust their star-making materials within a relatively short cosmic time span. The party will eventually end when the fuel runs out. At current consumption rates, both galaxies will burn through their available gas in just a few 100 million years. That sounds like a long time, but it's incredibly brief compared to the billions of years that normal galaxies spend gradually converting their gas into stars. This shortened timeline creates an inevitable countdown to stellar starvation. Once the gas supplies are exhausted, star formation will drop to nearly zero. The brilliant blue colors will fade as massive stars age and die without being replaced by new generations. The galaxies will enter a post-starburst phase dominated by stellar remnants. The collision that triggered this amazing stellar renaissance also guaranteed its eventual end. By compressing and consuming gas so efficiently, the antennae have traded long-term sustainability for short-term spectacular performance. They chose to burn bright rather than burn long, creating one of the universe's most impressive but temporary stellar fireworks displays. Beyond all the spectacular star formation lies an even more dramatic transformation happening to the material between stars. The galactic collision has created invisible shock waves that heat ordinary gas to temperatures more extreme than the cores of most stars. This superheated material glows with X-ray energy completely invisible to human eyes. Normal gas drifting through space maintains temperatures just a few degrees above absolute zero. It's incredibly cold and thin, posing no threat to anything it encounters. But when two galaxies collide at hundreds of kilometers per second, that gentle material becomes a cosmic blowtorch. The collision creates shock fronts that compress and heat gas throughout both galactic systems. These shock waves travel at speeds that instantly transform cold interstellar material into million-degree plasma. It's like turning a gentle breeze into a blast furnace through pure gravitational violence. This shock heating affects every gas cloud in both galaxies simultaneously. Material that spent billions of years drifting peacefully through space suddenly finds itself heated to temperatures that would vaporize any known substance. The collision transformed both galaxies into cosmic pressure cookers operating at impossible temperatures. The collision shattered the orderly gas motion that characterized both original spiral galaxies. What once flowed smoothly in organized patterns has exploded into chaotic turbulence that mixes material throughout both galactic systems. This cosmic stirring process redistributes gas on scales never seen in normal galaxies. Turbulence in space works similarly to turbulence in flowing water. Smooth streams break down into eddies, swirls, and chaotic mixing patterns. But galactic turbulence operates on scales that dwarf terrestrial comparison. Individual turbulent cells can span thousands of light years. This turbulent mixing serves multiple purposes in the collision process. It helps compress gas into star-forming densities by creating random collisions between gas streams. It also distributes energy from the collision throughout both galactic systems, ensuring that the gravitational violence affects every corner of both galaxies. The turbulence also accelerates chemical mixing between the two galactic systems. Gas that originated in one galaxy gets stirred together with material from the other, creating a blended composition that reflects contributions from both collision partners. Cosmic chaos becomes a giant mixing bowl. The collision is simultaneously creating and destroying the conditions necessary for star formation. While some regions experience compression that triggers stellar birth, Others suffer destruction of the delicate molecular structures needed for stars to form. The violence breaks apart the cosmic chemistry required for stellar nurseries. Molecular clouds represent the coolest, densest reservoirs of gas in normal galaxies. These clouds contain complex molecules like carbon monoxide and water that can only exist at very low temperatures. They provide the ideal conditions for gravity to gather material into star-forming clumps. But shock waves and intense radiation from the collision are tearing these molecular structures apart. High-energy photons break the chemical bonds that hold molecules together, converting organized molecular gas back into simple atoms. It's cosmic chemistry running in reverse. This molecular destruction competes directly with star formation enhancement in different regions of both galaxies. Some areas benefit from compression effects that aid stellar birth. Others suffer molecular disruption that prevents stars from forming despite having adequate raw materials. The collision creates a complex patchwork of creation and destruction. Tiny dust grains scattered throughout both galaxies have become crucial players in redistributing energy from the collision. These microscopic particles absorb starlight from newly formed massive stars and convert that energy into infrared heat radiation. The dust transforms both galaxies into cosmic space heaters. Cosmic dust consists of tiny solid particles, smaller than smoke particles in Earth's atmosphere. Under normal conditions, this dust drifts invisibly through space, occasionally blocking small amounts of starlight. But the collision has dramatically increased both the amount of dust and the intensity of starlight heating it. Massive stars being born throughout the collision zone flood their surroundings with intense ultraviolet and visible light. When this radiation hits dust particles, it gets absorbed and re-emitted as infrared heat. The more intense the star formation, the more the dust glows with thermal energy. This dust heating makes both galaxies much brighter in infrared wavelengths than normal spiral galaxies. The collision has created an efficient energy distribution system that captures starlight and broadcasts it as heat throughout both galactic systems. Every dust grain becomes a tiny cosmic radiator. Throughout the collision zone, powerful outflows of hot gas are streaming away from star-forming regions at incredible velocities. These stellar winds and supernova-driven flows carve enormous cavities in the surrounding material, creating a Swiss cheese structure throughout both galaxies. Young, massive stars generate powerful stellar winds that blow material away from their birth sites at speeds of thousands of kilometers per second. When these stars die as supernova, they create even more powerful explosions that blast hot gas outward at a significant fraction of light speed. These outflows don't just remove material from their immediate vicinity. They create expanding bubbles of hot, low-density gas that can grow to sizes larger than our entire solar system. Multiple bubbles often merge together, creating vast cavities carved out of the galactic medium. The outflow process removes material that might otherwise participate in future star formation. It's a negative feedback mechanism that gradually reduces the gas supply available for continued stellar birth. The collision triggered intense star formation, but those same stars are now working to shut down their own production line. Each galaxy brought its own unique chemical signature to this collision, reflecting billions of years of independent stellar evolution. The gravitational chaos is now mixing these distinct chemical histories together, creating a blended composition that combines elements from both galactic lineages. Different regions within galaxies typically show variations in their chemical makeup. Inner regions tend to be enriched with heavy elements produced by many generations of stars. Outer regions remain more pristine, retaining compositions closer to the original hydrogen and helium that filled the early universe. The collision is stirring together material from many different galactic environments simultaneously. Gas from the metal-rich central regions of one galaxy gets mixed with pristine outer material from the other. The result is a chemical blend that neither galaxy could achieve through internal processes alone. This mixing process accelerates the chemical evolution of both galactic systems. Instead of slowly enriching their gas supplies through internal stellar recycling, the collision forces rapid redistribution of elements throughout both galaxies. Cosmic violence becomes a catalyst for accelerated chemical evolution. Hidden throughout the collision zone are complex carbon-based molecules that create distinctive fingerprints in infrared observations. These polycyclic aromatic hydrocarbons, known as PAs, absorb ultraviolet starlight and re-emit characteristic infrared radiation that serves as a tracer for star formation activity. PAs are among the most complex molecules found in space. They consist of carbon atoms arranged in ring structures similar to the aromatic compounds found in petroleum and coal on Earth. These cosmic molecules can survive in the harsh environment of space and respond predictably to stellar radiation. When ultraviolet light from hot, massive stars hits PHH molecules, it excites them to higher energy states. As they return to their ground states, they emit infrared radiation at very specific wavelengths. This creates a molecular fingerprint that astronomers can detect across cosmic distances. The PAH emission throughout the antennae collision serves as a sensitive tracer for regions where massive stars are actively forming. The strength of PAH features in infrared spectra directly correlates with the intensity of nearby star formation. These molecules become cosmic beacons announcing stellar birth. Radio telescopes detecting carbon monoxide emission can map the distribution of cold molecular gas throughout both colliding galaxies. This simple molecule serves as a reliable tracer for the raw material available for future star formation, revealing where stellar birth might continue as the collision evolves. Carbon monoxide molecules emit radio waves at very specific frequencies when they undergo rotational transitions. These transitions occur commonly in the cold molecular clouds where star formation takes place. Radio telescopes can detect this emission and use it to map gas distribution with remarkable precision. The strength of carbon monoxide emission directly indicates how much cold molecular gas exists in each region of both galaxies. Bright CO emission marks areas with abundant star-forming material. Weak or absent CO emission reveals regions where gas supplies have been exhausted or disrupted. CO observations of the antennae show a complex pattern reflecting the collision's impact on gas distribution. Some regions show enhanced CO emission where compression has concentrated molecular material. Others show depleted CO levels where shock heating has destroyed molecular structures or where gas has been consumed by star formation. Silhouetted against the brilliant star-forming regions are dark lanes where dust concentrations block visible starlight. These dust lanes trace the densest concentrations of solid particles throughout both galaxies, creating a road map of where material has been compressed and redistributed by the collision. Cosmic dust becomes visible not by emitting its own light, but by blocking light from sources behind it. When dense concentrations of dust particles lie between bright stellar regions and Earth, they create dark lanes or patches that appear empty in visible light photographs. The dust lanes in the antennae collision are not randomly distributed. They follow specific patterns that reflect how the gravitational encounter has redistributed solid material throughout both galactic systems. The lanes often trace spiral arm remnants or mark boundaries between different collision zones. These dust concentrations also indicate potential sites for future star formation. Dense dust lanes often mark regions where gas compression has not yet progressed far enough to trigger stellar birth, but where conditions are favorable for eventual star formation. The dark lanes map tomorrow's stellar nurseries. The intense star formation triggered by the collision is gradually removing gas from both galaxies through a cosmic cleaning process that will eventually shut down stellar birth entirely. Stellar winds and supernova explosions are blowing material out of both galactic systems at such high velocities that it will never return. This gas removal process, called galactic outflow, represents one of the most important consequences of the collision. The massive stars being born at unprecedented rates are simultaneously consuming the gas needed for their formation and blowing away the raw materials for future generations. The outflowing material escapes both galaxies entirely, carrying away metals and heavy elements produced by stellar nucleosynthesis. This represents a permanent loss of both raw materials and processed elements from both galactic systems. The collision is slowly sterilizing both galaxies. Eventually, this gas loss will bring the starburst phase to an end. Once enough material has been blown away, neither galaxy will have sufficient gas reserves to sustain high rates of star formation. The collision that triggered the greatest stellar baby boom in either galaxy's history will ultimately ensure that no future baby booms can occur. Our eyes detect only a tiny fraction of the light coming from the Antennae Galaxies. What we call visible light represents just one small slice of a much larger electromagnetic spectrum. The collision is broadcasting its story across dozens of different types of light that remain completely invisible to human vision. Each type of light carries different information about what's happening in the collision zone. Blue and pink visible light shows us where new stars are being born, but infrared light reveals star formation hidden behind dust clouds. X-rays expose hot gas heated by the collision. Radio waves map the distribution of cold hydrogen gas. Scientists call this approach multi-wavelength astronomy. Instead of looking at cosmic objects through just one window, they observe the same target using many different types of light simultaneously. It's like having multiple witnesses to the same cosmic crime scene. The Antennae Galaxies have been studied across virtually every part of the electromagnetic spectrum, from high-energy gamma rays to low-energy radio waves. Each observation adds another piece to the puzzle. Together, these different wavelengths create the most complete picture possible of what happens when galaxies collide. Regular visible light photography provides the foundation for understanding the antenna collision. The same type of light that allows human eyes to see the world around us also reveals the most dramatic features of this galactic encounter. These familiar colors tell an immediately recognizable story. Blue regions throughout both galaxies mark the locations of hot, newly formed massive stars. These stellar giants burn at temperatures that produce brilliant blue-white light. The brighter the blue, the more intense the star formation occurring in that region. Pink and red emission traces where those same hot stars are energizing surrounding gas clouds. When ultraviolet light from massive stars hits hydrogen gas, it causes the hydrogen to glow with characteristic colors. Pink marks active stellar nurseries where gas is being ionized by nearby star formation. The combination of blue star clusters and pink gas clouds creates a visual map of where the collision is triggering the most dramatic stellar birth. Visible light observations provide an intuitive, immediately understandable portrait of cosmic violence transforming into cosmic creation. Much of the most intense activity in the Antennae collision remains hidden from visible light observations. Cosmic dust throughout both galaxies blocks our view of many star-forming regions, creating dark lanes that appear empty in normal photographs. Infrared observations reveal what's really happening in these seemingly vacant areas. Dust grains absorb visible starlight and re-emit that energy as infrared radiation, essentially converting optical light into heat. This process makes dust-obscured regions much brighter in infrared wavelengths than they appear in visible light. Infrared telescopes can peer through the dust to detect hidden stellar nurseries. Space-based infrared observatories reveal that some of the most vigorous star formation in the antennae is completely invisible to optical telescopes. Regions that look dark and empty in visible light turn out to be blazing stellar factories when observed in infrared wavelengths. The infrared excess also tells astronomers that the collision has stirred up enormous amounts of dust throughout both galaxies. This dust heating represents one of the clearest signatures that we're witnessing an active galactic collision rather than two normal, undisturbed spiral galaxies. X-ray observations reveal the most violent aspects of the galactic encounter that remain completely invisible at other wavelengths. X-rays are produced by extremely hot gas and by exotic stellar remnants like neutron stars and black holes. These high-energy observations expose the collision's most energetic processes. The collision heated gas throughout both galaxies to temperatures of millions of degrees. Normal gas in space is extremely cold, but shock waves from the galactic encounter compressed and heated material to temperatures that produce X-ray emission. This hot gas traces the most violent regions of the collision. X-ray telescopes also detect individual compact objects within the collision zone. Neutron stars and black holes that are actively feeding on nearby material emit characteristic X-ray signatures. The collision environment provides ideal conditions for these exotic objects to reveal themselves through high-energy radiation. X-ray observations complete the temperature story of the collision. While visible light shows us moderate temperature stars and infrared reveals cool dust, X-rays expose the hottest components of the system. Together, these observations map temperatures ranging from near absolute zero to millions of degrees. Radio wave observations reveal components of the antennae that remain completely undetectable at shorter wavelengths. Cold hydrogen gas, the raw material for future star formation, emits radio waves at very specific frequencies. Radio telescopes can map this fuel supply with incredible precision. Hydrogen atoms in space occasionally undergo a quantum transition that produces radio emission at a frequency of 1420 MHz. This transition happens rarely for any individual atom, but space contains so much hydrogen the combined signal becomes easily detectable by sensitive radio telescopes. Radio observations also trace carbon monoxide molecules that serve as markers for even colder molecular gas. This molecular gas represents the immediate feedstock for star formation. Radio maps show exactly where future generations of stars will be born as the collision continues to evolve. The combination of hydrogen and carbon monoxide radio observations provides a complete census of the gas supplies available for continued star formation. These radio maps reveal whether the collision is running out of fuel or still has abundant resources for future stellar birth. The Hubble Space Telescope's location above Earth's atmosphere allows it to capture images with resolution impossible for ground-based observatories. This crystal-clear vision can separate individual star clusters and stellar nurseries that appear blended together in less detailed observations. Hubble's precision reveals the fine structure of the collision. Atmospheric turbulence constantly blurs ground-based telescopic images, limiting the smallest details that can be resolved. Hubble operates in the vacuum of space, eliminating this atmospheric interference. The result is images sharp enough to distinguish features just a few light years across in the distant Antennae Galaxies. This exceptional resolution allows astronomers to study individual superstar clusters within the collision zone. Each cluster can be analyzed separately to determine its age, mass, and stellar content. Hubble transforms the antenna from a single blended system into thousands of individually resolvable stellar nurseries. Hubble's sharp vision also tracks how the collision has evolved over time. By comparing images taken years apart, astronomers can measure the motion of stars and gas throughout the system. This time-lapse capability turns Hubble into a cosmic motion picture camera documenting galactic collision in slow motion. The Atacama Large Millimeter Array represents the ultimate tool for studying the cold molecular gas where stars are actually born. ALMA's unprecedented resolution at millimeter wavelengths can map the distribution and motion of star-forming gas with detail impossible at any other wavelength. This reveals the collision's most intimate stellar birth processes. Millimeter waves penetrate dust clouds that block visible and infrared light, allowing ALMA to observe directly into the hearts of stellar nurseries. The telescope array can trace carbon monoxide and other molecules that serve as thermometers and speedometers for the gas destined to become stars. ALMA observations reveal the internal structure of molecular clouds throughout the collision zone. Individual clouds can be mapped to show exactly how gravitational compression is organizing gas into the dense cores that will collapse to form new stars. It's like watching stellar assembly lines in action. The exceptional resolution also allows ALMA to measure gas velocities throughout the collision system. These velocity measurements trace how the galactic encounter is stirring and compressing molecular gas, providing direct evidence for the mechanisms that trigger enhanced star formation during galactic collisions. No single type of observation can tell the complete story of the antenna collision. Scientists use sophisticated computer models to combine data from across the entire electromagnetic spectrum into one unified picture. This process, called spectral energy distribution modeling, synthesizes all available information into a comprehensive understanding. The models start with the assumption that the collision contains stellar populations of different ages, masses, and evolutionary states. Each stellar population contributes differently to the total light output across all wavelengths. By comparing model predictions with actual observations, astronomers can determine the properties of each stellar component. This modeling process reveals details impossible to determine from any single wavelength. The total stellar mass, the rate of current star formation, the amount of dust, and the ages of different stellar populations all emerge from careful analysis of multi-wavelength data combined with theoretical models. The unified models also allow astronomers to predict how the collision will evolve in the future. By understanding the current state of both galaxies across all wavelengths, scientists can forecast what the antennae will look like millions of years from now as the merger continues to unfold. Light waves can vibrate in different orientations, and some astronomical objects preferentially emit light vibrating in specific directions. This polarized light carries information about magnetic fields threading through the collision zone. Polarization observations reveal invisible magnetic highways that channel gas flow throughout both galaxies. Dust grains in space tend to align themselves with local magnetic field directions. When starlight passes through these aligned dust particles, it becomes slightly polarized. The degree and direction of polarization maps the strength and orientation of magnetic fields throughout the galactic system. Magnetic fields play important roles in controlling how gas flows during galactic collisions. They can either help channel gas towards star-forming regions or prevent gas from collapsing by providing magnetic pressure that resists gravitational compression. Polarization observations reveal these invisible influences. The magnetic field maps show how the collision has twisted and amplified the original magnetic structures in both galaxies. What started as orderly field patterns in the original spiral galaxies has been transformed into complex, tangled configurations that reflect the chaos of the ongoing gravitational encounter. The Antennae collision is happening so slowly that changes become visible only over periods of years or decades. Astronomers have been observing this system for more than 30 years, creating a unique time-lapse record of galactic evolution in progress. This long-term monitoring reveals how the collision continues to evolve. Stellar birth rates fluctuate as different regions of the collision experience varying levels of gravitational compression. Multi-decade observations can track these variations, revealing how star formation responds to the changing dynamics of the gravitational encounter. The extended observational baseline also allows astronomers to measure the actual motion of structures within the collision zone. Tidal tails, stellar streams, and even individual star clusters can be tracked as they move in response to the complex gravitational forces operating throughout the system. This temporal dimension adds crucial information that cannot be obtained from single-epoch observations. The collision becomes a living, evolving system rather than a static snapshot. Long-term monitoring transforms the antennae into a laboratory for studying galactic evolution in real time. When all these different types of observations are combined, they create an unprecedented three-dimensional understanding of how galactic collisions work. No other collision system in the universe has been studied across so many wavelengths with such extraordinary detail. The antennae represent our most complete laboratory for collision physics. The multi-wavelength approach reveals that the collision is not a simple uniform event. Different processes dominate in different regions of the system. Some areas are experiencing intense star formation, others are being stripped by tidal forces, and still others are being heated by shock waves from the encounter. This comprehensive view also shows how different physical processes are connected throughout the collision. Star formation triggered by gas compression creates stellar winds that heat surrounding material. Hot gas detected in X-rays interacts with cold molecular gas mapped by radio telescopes. Everything is interconnected. The complete electromagnetic spectrum portrait of the antennae provides a blueprint for understanding galactic collisions throughout the universe. When astronomers discover similar systems at greater distances, they can interpret those observations using the detailed knowledge gained from studying the nearby antennae across all possible wavelengths of light. Scattered throughout the antennae collision zone are cosmic cities unlike anything found in normal galaxies. These stellar metropolises contain more stars packed into small regions than most entire galaxies possess. Astronomers call them young massive clusters, and they represent star formation pushed to its absolute physical limits. Each cluster contains between 100,000 and 1 million individual stars crammed into regions just a few light years across. To put this in perspective, our Sun's nearest neighbor sits more than 4 light years away. In these clusters, stars are packed thousands of times more densely than in our galactic neighborhood. The collision created ideal conditions for these monster clusters to form. When shock waves compressed enormous gas clouds all at once, instead of fragmenting into many small star-forming regions, entire clouds collapsed together. The result is stellar birth on a scale that creates some of the most crowded neighborhoods in the universe. These clusters are so massive and bright that individual examples outshine entire normal galaxies. They represent the ultimate expression of the collision's ability to trigger star formation. The gravitational chaos didn't just create more stars than usual. It created stellar cities that redefine what's possible in cosmic architecture. What prevents hundreds of thousands of stars from simply drifting apart once they're born in these incredibly dense clusters? The answer lies in their tremendous combined mass. These stellar collections are gravitationally bound systems, meaning their own gravity is strong enough to hold every member star in place permanently. Most star-forming regions in normal galaxies are too small and lightweight to hold onto their stellar residence. Once stars finish forming, they gradually drift away from their birth sites and disperse throughout the galaxy. These loose associations typically dissolve within a few million years. But the massive clusters in the antennae are different. Their combined gravitational pull creates a cosmic prison that no individual star can escape. Even if a star gets kicked to high speeds by gravitational interactions with its neighbors, the cluster's gravity is strong enough to prevent permanent escape. This gravitational binding ensures that these stellar cities will survive for billions of years. Long after the collision has ended and the galaxies have merged completely, these clusters will remain as permanent monuments to the violence that created them. Gravity has built stellar communities designed to last for cosmic eternity. Inside these crowded stellar cities, something remarkable happens over time. The most massive stars gradually sink toward the center, while lighter stars get pushed toward the outer regions. This cosmic sorting process, called mass segregation, organizes each cluster into distinct neighborhoods based on stellar weight. This segregation occurs through countless gravitational interactions between cluster members. When stars pass close to each other, they exchange energy and momentum. Heavier stars tend to lose energy in these encounters, causing them to sink deeper into the cluster's gravitational well. The process resembles sediment settling in a jar of muddy water. Heavy particles sink to the bottom while lighter material floats toward the surface. But in stellar clusters, this settling happens through gravitational interactions rather than buoyancy effects. Mass segregation transforms each cluster from a random mix of stellar types into an organized stellar society. The core becomes dominated by massive blue giants and red supergiants. The outer regions fill with lighter, longer-lived stars like our Sun. Gravity creates cosmic social stratification based purely on stellar mass. The most massive stars in these clusters undergo dramatic evolutionary phases that normal stellar neighborhoods never experience. These stellar monsters become Wolf-Rayet stars, extreme objects that blow away their outer layers through incredibly powerful stellar winds. They represent stellar evolution pushed to its breaking point. Wolf-Rayet's stars form when the most massive cluster members burn through their nuclear fuel so rapidly that they shed their outer hydrogen layers completely. What remains is a naked stellar core burning helium and heavier elements at temperatures exceeding 50,000 degrees. These exposed cores generate stellar winds of unimaginable power. These stellar winds carry away material at speeds reaching thousands of kilometers per second. The outflowing gas creates expanding bubbles around each Wolf-Rayet star that can grow larger than our entire solar system. It's like having cosmic geysers scattered throughout the stellar city. The Wolf-Rayet phase represents the final, desperate attempt by massive stars to shed excess weight before their inevitable collapse. These stellar giants are literally blowing themselves apart through the sheer intensity of their nuclear burning. The collision created conditions for stellar evolution at its most extreme and unstable. The massive stars in these clusters don't die quietly. When they exhaust their nuclear fuel, they explode as supernovae with enough energy to influence their entire stellar neighborhood. Multiple supernova explosions create chain reactions that reshape the entire cluster environment over relatively short timescales. Each supernova explosion releases more energy than our Sun will produce during its entire 10 billion-year lifetime. When this energy gets released in an already crowded stellar environment, it creates shock waves that propagate throughout the cluster. These shock waves can trigger additional stellar deaths in neighboring massive stars. The chain reaction effect means that supernova explosions don't occur randomly throughout the cluster's lifetime. Instead, they tend to cluster together in time, creating periods of intense stellar violence followed by relative calm. It's like cosmic fireworks displays that come in concentrated bursts. These supernova chain reactions also remove significant amounts of material from each cluster. The combined explosions can blow away any remaining gas and dust, leaving behind a population of stars swimming in hot, low-density plasma created by the stellar explosions. The most massive cluster members gradually destroy their own birth environment. Every massive star in these clusters generates powerful stellar winds throughout its lifetime. When hundreds of thousands of these winds combine together, they create cluster-scale outflows that can influence regions far beyond the cluster boundaries. These combined winds become stellar hurricanes operating on galactic scales. Individual stellar winds from massive stars already carry tremendous energy and momentum. But when thousands of such winds combine within the small volume of a dense cluster, they create collective outflows that dwarf anything produced by isolated stars in normal galactic environments. These cluster winds carve enormous cavities in the surrounding galactic medium. The combined outflow can create bubbles of hot, low-density gas that extend for hundreds of light years in all directions. It's like having cosmic leaf blowers operating continuously at maximum power. The cluster winds also prevent new star formation in their immediate vicinity by blowing away any gas that might otherwise collapse to form additional stars. The stellar cities become so effective at clearing their surroundings that they essentially sterilize large regions of both galaxies against future stellar birth. When the most massive stars in these clusters die, they don't simply disappear. They leave behind compact remnants like neutron stars and black holes. These exotic objects, denser than anything else in the universe, gradually sink toward the cluster center through gravitational interactions. The cores become graveyards for stellar giants. Neutron stars contain the mass of our entire Sun compressed into spheres just 20 kilometers across. Black holes represent regions where gravity has become so strong that nothing Not even light can escape. Both types of objects pack incredible mass into tiny volumes. The mass segregation process that sorts living stars by weight also affects these stellar corpses. Neutron stars and black holes are so dense that they inevitably sink to the cluster center, creating concentrated populations of the universe's most extreme objects in the most crowded stellar environments. Some of these compact objects capture normal cluster stars as companions, creating X-ray binary systems that shine across the electromagnetic spectrum. The cluster cores become populated by some of the most energetic and exotic objects known to astronomy. Dense stellar cities become showcase environments for extreme physics. The extreme crowding in these stellar cities creates a gradual death spiral that will eventually destroy most of the clusters. As stars interact gravitationally over millions of years, the clusters slowly lose energy and spiral inward toward the centers of their host galaxies. This process, called dynamical friction, represents gravity's ultimate victory over stellar architecture. Dynamical friction works like cosmic air resistance. As massive clusters orbit through the galaxy, they interact gravitationally with surrounding stars and gas. Each interaction removes a small amount of energy from the cluster's orbit, causing it to spiral gradually inward toward the galactic center. The process operates on timescales of hundreds of millions of years, but it's relentless and irreversible. Dense clusters experience stronger dynamical friction than lightweight ones because their greater mass creates more gravitational interactions with their surroundings. The most impressive stellar cities face the greatest risk of eventual destruction. Eventually, many of these clusters will spiral all the way into the merged galaxy's central region, where tidal forces will tear them apart completely. The stellar cities that survive the original collision will ultimately be destroyed by their own success in creating massive, gravitationally influential stellar communities. Not all the massive clusters will survive long enough to spiral into the galactic center. Some face immediate destruction from tidal forces operating throughout the collision zone. These galaxy-scale gravitational forces can overcome even the strong internal gravity that holds cluster members together, dispersing stellar cities back into the general galactic population. Tidal forces arise whenever one part of an object experiences significantly different gravitational attraction than another part. For clusters orbiting in the chaotic gravitational environment of colliding galaxies, different regions of each cluster feel different amounts of pull from the various massive components of the system. If tidal forces become stronger than the cluster's internal gravity, the stellar city gets stretched apart. Stars on one side get pulled away while stars on the other side experience different acceleration. The cluster becomes elongated and eventually dissolves completely into individual stars scattered throughout the galaxy. This tidal disruption process converts bound stellar clusters back into field stars that orbit individually throughout the merged galaxy. It's cosmic urban renewal that demolishes stellar cities and returns their residents to suburban galactic neighborhoods. Galaxy-scale forces ultimately overpower even the most gravitationally bound stellar communities. Each massive cluster contains stars of slightly different ages, creating a cosmic archaeological record of how star formation proceeded during the collision. This age spread reveals whether stellar birth happened all at once or extended over longer periods, providing crucial information about collision dynamics. Star formation within individual clusters doesn't happen instantaneously. Even with ideal conditions created by galactic collision, it takes time for gas to collapse and condense into stellar objects. The process can extend over several million years, creating measurable age differences between cluster members. Astronomers can measure stellar ages by studying the colors and brightnesses of cluster stars. Newly formed stars appear blue and extremely bright, while slightly older stars have evolved to different colors and luminosities. The range of stellar properties within each cluster maps the timeline of stellar birth. This age information helps astronomers understand how the collision triggered star formation in different regions and at different times. Some clusters show evidence for rapid, synchronized stellar birth. Others reveal more extended formation periods. The stellar ages become a fossil record of collision dynamics preserved in the properties of individual stars. Some of the massive clusters in the Antennae collision might survive all the destructive forces operating around them and evolve into objects very similar to the globular star clusters found orbiting our own Milky Way galaxy. These ancient stellar communities represent what collision-born clusters might look like billions of years in the future. Globular clusters are among the oldest objects in our galaxy. They contain stars that formed when the universe was young, packed into spherical arrangements that have survived for more than 10 billion years. They represent stellar cities that have endured since cosmic antiquity. The most massive and tightly bound clusters in the antennae show properties very similar to young globular clusters. If they can survive the various destructive processes operating during and after the galactic merger, they might evolve into the globular cluster systems that future astronomers will observe orbiting the merged galaxy. This connection suggests that globular clusters throughout the universe might represent the surviving remnants of ancient galactic collisions. The violent encounters that seem so destructive might actually be necessary for creating the long-lived stellar communities that populate mature galaxies. Today's collision violence becomes tomorrow's ancient stellar architecture. Every massive cluster in the Antennae collision carries a unique chemical signature that reflects the specific conditions present when and where it formed. These chemical fingerprints preserve information about the collision process that would otherwise be lost as the merger continues to evolve over cosmic time. Different regions of the colliding galaxies had different chemical compositions before the encounter began. Intergalactic regions were enriched with heavy elements produced by previous generations of stars, while outer regions remained more chemically primitive. The collision mixed these different compositions together. Each cluster's chemical makeup reflects the specific blend of materials available at its formation site. Clusters that formed from gas originally located in the inner regions of either galaxy show different element ratios than clusters born from outer galactic material or from mixed compositions created by collision turbulence. These chemical differences allow astronomers to trace the collision's impact on material distribution throughout both galaxies. The cluster compositions become a chemical archaeological record that preserves information about pre-collision galactic structure and collision-induced mixing processes. Each stellar city carries the chemical memory of its violent birth environment. Eventually, the dance must end. The two galactic centers that have been circling each other for hundreds of millions of years will finally merge into a single, massive core. This cosmic wedding will create one giant galactic heart, where two separate hearts once beat with independent rhythms. The merger of galactic cores represents the climax of the entire collision process. For hundreds of millions of years, both galaxies have maintained separate identities despite their gravitational embrace. But as their orbits decay and they spiral ever closer together, that separation becomes impossible to maintain. When the cores finally touch, their combined mass creates a gravitational field stronger than either galaxy possessed individually. The merged core becomes the new gravitational anchor that will hold the entire system together. It's like two separate kingdoms uniting under one crown. This core merger marks the point of no return for both galactic systems. Before this moment, the galaxies remained distinct entities locked in gravitational combat. After this merger, they become one unified system with a single gravitational center governing the motion of every star in the combined galaxy. The violent collision that created such spectacular chaos will eventually settle into something surprisingly orderly. Over hundreds of millions of years, the scrambled stellar orbits will gradually organize themselves into a smooth, predictable arrangement. Astronomers call this cosmic settling process relaxation. During the collision, every star's orbit got disrupted by the complex gravitational forces from both galaxies. Stars that once followed neat, circular paths around their home galaxy suddenly found themselves on wild, elongated trajectories that took them far from their original neighborhoods. But gravity never stops working. Over vast periods of time, gravitational interactions between stars will gradually smooth out these chaotic orbits. High-energy orbits will lose energy through stellar encounters. Low-energy orbits will gain energy from the same interactions. Eventually, the system reaches equilibrium. The final result will be a galaxy where stellar orbits are completely randomized but perfectly balanced. No trace of the original spiral structure will remain. Instead, stars will follow smooth, elliptical paths that create the characteristic shape of a giant elliptical galaxy. Hidden at the center of each original galaxy lurks a supermassive black hole containing millions of times the mass of our Sun. These cosmic monsters will eventually merge together, creating one ultimate predator that dominates the heart of the combined galaxy system. Both black holes will spiral toward each other, just like their host galaxies, but on much smaller scales. As they get closer together, they'll begin orbiting each other faster and faster, creating a binary black hole system. This cosmic dance releases tremendous amounts of energy in the form of gravitational waves. Gravitational waves are ripples in space-time itself, created when massive objects accelerate through gravitational fields. The merging black holes will generate waves so powerful they'll be detectable by sensitive instruments across the universe. The final merger will create one of the most energetic events possible in cosmic physics. The combined black hole will contain more mass than either individual monster possessed originally. This single, ultimate predator will anchor the merged galaxy's core, influencing the motion of stars across hundreds of thousands of light years. Two cosmic monsters become one, even more terrifying apex predator. The incredible star formation that made this collision so spectacular cannot continue indefinitely. The galaxies are consuming their gas supplies at such extreme rates that they're guaranteed to exhaust their star-making fuel within a relatively short cosmic timespan. Stellar starvation is inevitable. Normal galaxies carefully manage their gas reserves, forming stars at sustainable rates that allow stellar birth to continue for billions of years. But the collision triggered a cosmic feeding frenzy that burns through available materials at unsustainable speeds. It's like spending your entire savings account in a single shopping spree. As gas supplies dwindle, star formation rates will drop dramatically. Fewer and fewer stellar nurseries will have enough raw material to trigger new stellar birth. The brilliant blue regions that currently dominate both galaxies will gradually fade as massive stars age and die without being replaced. Eventually, star formation will drop to nearly zero throughout the merged system. The galactic collision that triggered the most intense stellar baby boom in either galaxy's history will ultimately ensure that no future baby booms can occur. Cosmic violence creates its own sterilization. As star formation winds down throughout the merged galaxy, the entire system will undergo a dramatic color transformation. The brilliant blue light that currently dominates both collision partners will gradually fade to red as the galaxy ages into cosmic middle age. Blue light comes from hot, massive stars that live fast and die young. These stellar giants burn their nuclear fuel so rapidly that they typically survive for only millions of years before exploding as supernovae. When star formation stops, no new blue giants get born to replace the ones that die. Red light comes from smaller, cooler stars that burn their fuel much more slowly and can survive for billions of years. These stellar senior citizens will gradually dominate the galaxy's light output as the short-lived blue giants fade away through natural stellar death. This color evolution serves as a cosmic clock that tracks the galaxy's aging process. Blue galaxies represent cosmic youth and vigorous star formation. Red galaxies represent cosmic maturity and stellar old age. The Antennae system will transition from vibrant youth to sedate middle age over the next billion years. Not everything involved in this cosmic collision will end up in the final merged galaxy. The spectacular tidal tails that gave the antennae their distinctive appearance contain material that will never return home. These cosmic exiles are permanently banished to the void between galaxies. The tidal streams stretching away from both galaxies contain billions of stars and vast amounts of gas that were ripped away during the collision's most violent phases. Some of this material follows orbits that might eventually curve back toward the merger site, but much of it is traveling too fast to ever return. This represents a permanent loss of material from both galactic systems. Stars and gas that spent billions of years as productive galactic citizens now drift through intergalactic space as cosmic refugees. They'll never again participate in the organized stellar communities that characterize bound galactic systems. The lost material also carries away heavy elements produced by previous generations of stars within both galaxies. This chemical enrichment gets dispersed into the thin web of matter that connects galaxy clusters across cosmic distances. The collision enriches the universe at the expense of the colliding galaxies themselves. The merger process will create a galaxy much larger than either of the original spiral systems. Gravitational interactions during the collision scatter stars outward, creating a more extended stellar distribution than existed in either pre-collision galaxy. Violence breeds cosmic expansion. During the chaotic collision phases, many stars receive gravitational kicks that boost them to higher orbital energies. These energized stars move to larger orbits that carry them farther from the galactic center. It's like a cosmic billiard game where collisions scatter balls across a larger area. The scattering process affects stars throughout both galactic systems, not just those in the collision zone. Even stars that never directly experience strong tidal forces get their orbits altered through secondary gravitational interactions with other scattered stars. The disruption propagates throughout both galaxies. The final merged galaxy will span a much larger volume than the combined space occupied by both original spirals. What started as two compact, organized stellar systems transforms into one bloated, extended galaxy with stars scattered across much greater distances. Gravitational chaos creates cosmic urban sprawl. The beautiful spiral arms that originally defined both galaxies will be completely erased by the merger process. What emerges will be a giant elliptical galaxy with a smooth, featureless light distribution that shows no trace of the elegant spiral structure that existed before the collision. Spiral arms represent organized stellar traffic patterns where stars follow similar orbits around the galactic center. These orderly flows create the distinctive curved structures that make spiral galaxies so visually appealing. But collision chaos destroys this orbital organization completely. The merger randomizes stellar orbits throughout both galactic systems. Instead of following similar paths that create spiral patterns, stars end up on completely different orbital trajectories. Some stars move in one direction, others move in opposite directions, and still others follow paths tilted at various angles. This orbital randomization eliminates any possibility of maintaining spiral structure. The final galaxy will have a smooth, spherical shape with no internal patterns or organizational features. Two beautiful spiral galaxies transform into one featureless elliptical system that shows no memory of its original elegant architecture. Even billions of years after the merger completes, astronomical detectives will still be able to uncover evidence that this galaxy formed through a violent collision. The stellar populations and chemical compositions will preserve fossil evidence of the merger event long after all obvious signs of disruption have faded. Different stellar populations within the merged galaxy will retain slightly different chemical signatures reflecting their different origins. Stars that formed before the collision will show one set of element ratios. Stars born during the starburst phase will display different chemical fingerprints. These differences persist for billions of years. The merged galaxy will also contain stellar streams and substructures that trace back to the original collision event. Computer simulations show that tidal debris can remain detectable as coherent stellar groups for extremely long periods, even after the overall galaxy has relaxed into equilibrium. Future astronomers studying this system billions of years from now will be able to piece together the collision story by carefully analyzing stellar ages, chemical compositions, and subtle structural features. The violent encounter becomes a permanent part of the galaxy's archaeological record, preserved in the properties of individual stars. The transformation from violent collision to peaceful elliptical galaxy will take an enormous amount of time. Even after the cores merge and star formation ends, the galaxy will continue evolving and settling for billions of years before reaching true equilibrium. Cosmic peace arrives slowly. Gravitational relaxation operates on timescales that dwarf human comprehension. Individual stellar encounters happen rarely in the vast emptiness of space, so it takes enormous amounts of time for enough interactions to occur to smooth out all the orbital irregularities created by the collision. The merged galaxy will go through several evolutionary phases during this settling process. Early phases will show clear signs of recent merger activity. Intermediate phases will display gradual organization of stellar orbits. Final phases will achieve complete equilibrium with perfectly balanced stellar motion. Eventually, perhaps 10 billion years from now, the system will reach a state of complete dynamical equilibrium. Every star will follow a stable orbit determined by the smooth gravitational potential of the merged galaxy. The violent collision that created such dramatic disruption will have evolved into one of the universe's most stable and long-lived galactic systems.